Hello, I'm Professor Steve Miller. Today I want to talk about the Launder and Sharma model of 1974. This model takes and advances the K epsilon 2 equation models to the so-called low-Reynolds number models. It doesn't mean the flow overall is low-Reynolds number, it just means it doesn't use wall functions. In the previous talk, we talked about the K epsilon model with wall functions, which are so-called high-Reynolds number traditionally. Don't be confused about this within CFD codes and production. Now, of course, more powerful computers today, and certainly those coming out in the 70s and 80s, made use of wall functions. But with more computer power, we could reduce their use and make grids which are all the way to the wall and resolve the y plus distance of, say, 1 near the wall. If this was the first grid point and this was the wall. Once again, this is the distance from the wall and this is the x direction. And so the grids would fully resolve the viscous sublayer within the boundary layer. This, of course, requires much finer grids and much larger computational expense. Now, the idea behind these types of models to take the high Reynolds number K epsilon models and bring them to the wall was through a Taylor expansion for small y distances. And if we expand u prime, v prime, and w prime as, say, for u prime, a1y plus b1y squared, etc., and we do the same for v prime and w prime, we would have polynomials of this type, which we'd write in 75. Now, within these expansions, we might now calculate particular quantities. For example, u prime v prime bar, k, turbulent kinetic energy, the dissipation, which we previously defined, and the eddy viscosity with the boundary layer assumptions. Using 75 and the quantities which I just underlined, we can find equation 76, and we can find these same expansions. For example, for the Reynolds stress, turbulent kinetic energy, dissipation, and eddy viscosity. Here I've written all the first order terms, if you will, in the expansions from 75. Now, a quick review of our important equations. We have the equation for turbulent kinetic energy here, and we have an equation for dissipation of turbulent kinetic energy as the second equation. You'll notice that there's certain terms. In the high Reynolds number case, we set particular terms to 0. In this case, we don't. We need to seek, say, a particular form, especially for the d function and the f mu function. Let's look at the d function first and associate boundary conditions when we make this particular assumption. We first look at the d function and boundary conditions. At the wall, we would set turbulent kinetic energy to 0. Of course, this is true because velocity fluctuations are at the wall are 0 because there's no flux through the wall and no slip condition. Dissipation is not so simple usually, and we might set dissipation as epsilon equals 2a nu, which is the viscosity. Look up here in this particular model to track dissipation near the wall. We have k of 0, and so we may have to do something special with dissipation at the wall. Here we can look at A, and we define A as the limit as y going to 0 towards the wall of the turbulent kinetic energy divided by the distance to the wall squared. Now, A would be defined as the square of partial k to the half partial y at the wall, or, more simply, 1/2 of partial 2k partial y squared at the wall. So practically all k epsilon models are setting k to 0 at the wall. And they might, in many models today, set epsilon as 0 at the wall, which makes sense because, of course, nothing can be dissipating at the wall because it's a one-point statistic. But this means we need to modify d in the TKE equation here. This is effective dissipation now, after we set a particular d to set epsilon 0, and we would call the effective dissipation epsilon minus d at the wall only. We would then sub a series expansion of equation 76 here into our k equation, which we reviewed just now. If you do this, you'll find equation 77. You'll get nu, the viscosity times partial 2k of partial y squared, minus dissipation plus the d function, which is on the third order. Now, with partial 2k partial y squared, we'll have 2a plus the higher order terms with the dissipation of 0 at the wall. Then we can say that the limit, as y going to 0, of d will be equal to 2a. And through this method, we found a way to relate d with the function which we defined as a to enforce epsilon of 0 at the wall. D is most simply and often set after this analysis as either negative 2 mu of k over y squared or negative 2 mu, that's viscosity, times the square of partial k to the half over partial y. You'll have to know which particular model this form uses. These are the two most popular form, and of course, ones introduced by Launder and Sharma. The other function we haven't defined, of course, is f2 and e functions. Let's do this now. Epsilon close to the wall, that is not at the wall but very close to it, can be found from examination and simplification of the dissipation function equation. We'll have the viscosity times partial 2 epsilon partial y squared, which is dissipation, minus Ce2 f2 of epsilon squared over k plus e is 0 of order y. So we must choose, which is small I might mention. So we need to choose f2 and e to be something on the order of 1 for small distances of y to make 78 valid. If e is 0, then f2 will decay as y squared very much close to the wall. Many models calibrate f2 to decay with grid turbulent experiments. In practice, in boundary layers near the wall, we find that n, the decay of k near the wall, will go as about 2.5. Therefore, we would set f2 to be n plus 1 over n times 1 over c epsilon 2. We need to also look at this f mu function. We choose f mu so that its limit goes as equation 76 is reproduced. This is the ideas behind the Launder and Sharma model, the core ones at least, and I encourage you to look at the journal article to see the full development. It is indeed a low Reynolds number model. We set k and epsilon to be 0 at the wall, which is a very physical definition, but of course then we had to modify d and e, and we find an effective dissipation of epsilon minus d. And they propose the following modeling constants with our physical arguments we presented. They say f mu goes as exp of negative 3.4 over 1 plus ret divided by 50 squared. f1 they set to unity. f2 they set to unity minus 0.3 of exp to the negative ret squared. They set the d function to negative 2 nu of 2 squared of k over partial y squared, e to 2 nu t, that's viscosity and eddy viscosity, times partial 2u partial y squared. Also, you'll see that the particular constants, which were previously defined for the high-Reynolds number, are exactly the same values. And here they are for your reference, which we talked about in a previous lecture. You'll see the most familiar value of C mu of 0.09. Thanks very much for your time today. I'm Professor Steve Miller.